you want to do now? English. No problem. English. Biology. Eh? Chemistry again. Right, chemistry. Chemistry. All right, chemistry, please. Organic. What is it? What is it? Biology. Mm-mm. There is nothing in English. English is annoying. You know, it's pretty annoying. Pretty annoying. But it's very simple, actually. But just pretty annoying. Let me test us on something. Okay. Give me your past questions. All the subjects. Oh yeah, give me physics. Okay, have you done physics today? Um, Last year, Dr. Anosike stopped somewhere in electric field, and he should be moving to capacitors. You define electric field intensity, electric force, electric field intensity, electric potential. I'm sure he did that. Okay? Is he not the one that taught you electrostatic? Bring finger, oh yeah, charging an electroscope. I say charging an electroscope. What do you do? Number one. Uh-huh. 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 Charging an electroscope. Everybody sing. I said that is your number 3 question. Charging an electroscope. I say charging an electroscope. What do you do? Mm-hmm. 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 So if you do this, you've completely charged an electroscope. I'm sure people joining us, you might not know we are singing. Once we sing, we are singing questions we are going to sing in the hall. Go and study your electrostatics, study everything there. I strongly believe that 3 questions should come out from that area. I don't know why it's 3. Okay. What I will talk about will somewhat find I'll have to draw a cross link to electrostatics, but I'm sure we did electrostatics very well. What is the function of Van de Graaff generator? Ahem. Van de Graaff. I think is something like this. Van de Graaff generator. Kendi gula kuko na weekend na holiday. Have you heard of that word, Van de Graaff generator? If you have heard, just raise up your hand. I saw it in somebody's question. Sunday. Why did you carry my board? Come and drop my board where it is. So it's not blocking you or anything. It's obstructing you. I bring it this side. Bring it this side. Is it will it obstruct you this side? Van, is the where should I correct? Is there E somewhere? Where is E? Is there E here? Check now on Google. Is a special type of generator that produces electrostatic charges. Is a special type of generator that produces static charges. Okay, we're going to talk about just small thing you've known. Capacitors and capacitance. Say capacitors and capacitance. Say capacitors and capacitance. I think you've done it in secondary school. Okay. Just for 30 minutes, very short. Capacitors and capacitance. If you've known it, I'll give you a question to solve. Okay. What is a capacitor? So you don't need to copy. We are discussing. Oh, these NEPA people. What is a capacitor? Now I can transmit. Eh? A capacitor is a device. Say it. With two terminals. Used to store charges. Used to store charges. So what do we use a capacitor to do? Under electrostatics, there is another device you can use to store and transfer charges. What is the name of that device? Say electrosporus. Say electrosporus. Yes, electrosporus is a material. Is one of the oldest form of capacitor that can produce electrostatic charges. In fact, it can store and transfer charges. I say, what can store and transfer charges? Electrosporus. So, types of capacitor. We have fixed capacitor and variable what? Capacitor. We have fixed capacitor and variable capacitor. And we say that we use capacitors to do what? To store charges. To store charges. So under fixed capacitor, we have different types of fixed capacitor, but the most commonest one we are going to discuss is the ceramics type. That is the parallel plate capacitor. Can you boy? The parallel plate capacitor. That is the commonest. We have electrolytic. We have many, there are many. But the commonest one provided in our O level is the ceramics parallel plate capacitor. Now, this capacitor, can you hear me everywhere? Oh, Jehovah. You cannot hear me. I know you can hear me. Okay. I said that the parallel plate capacitor comprises of two metallic conductors of different polarity. I said it's, yeah, thank you. The commonest type of capacitor is the what? The parallel plate capacitor, just like this. And this is the diagram of a capacitor. See? Yes. Now, this capacitor is separated. Media, help me, zoom if you can. By a small distance called what? D. Now, this is a plate. This is another plate. This is okay, let's say this is positive and negative. This is an example of capacitor. You can see something like this. They write 5 UF. We have capacitors like this. Depending. So what do we use capacitors to do, class? We use them to store charges. So we are just to store charges. Okay. And the commonest type is the parallel plate capacitors. Okay, now what are the components? It has two metallic what? Plates of different polarity. One is positive, the other one is what? Negative. Separated by So what are we going to see in between the two parallel plates? Yes, we are going to see insulating material. Now, This insulating material is what is called the what? Dielectric material. It's called the what? Dielectric material. And the purpose of this dielectric material is to enhance, increase the capacitance of the capacitor. Say it again. 1, 2, ready, go. So what is the purpose of the dielectric material? To enhance or increase the capacitance of the capacitor. Now listen, you know it's a story. Don't worry, I'm not teaching physics. I'm a biology teacher. But listen. Capacitors used to store charge. Now, capacitance of a capacitor literally is the quantity of charge a capacitor can what? Store. You know, when you come to a resistor, what would you say? Resistance of a resistor. Inductor. Inductance of an inductor. Oh yeah? When you come to capacitor, what would you say? Capacitance of what? A capacitor. Capacitance. So what is capacitance now? The quantity of charge the capacitor can what? Store. The quantity of charge the capacitor can. So if I have a 5 microfarad capacitor and a 2 microfarad capacitor, which one stores more energy? Which one stores more charge? 5. So this one have a higher capacitance. What is the unit of capacitance? No, the unit is farads. The unit is what? Farads. But you know we have smaller units. Like the micro what? Farads. Do you know how to convert from microfarads to farads? No, Martin. Okay? So what are you going to do? 1 microfarad. If you are converting it to farads, can you gabo? 1 times 10 raised to power what? Minus 6 what? Farads. So we have microfarads, we have nanofarads, and we have what? Pico what? Farads. The other smaller units. Now, but mathematically, or actually, the capacitance of the capacitor is the quantity of charge stored by the capacitor to the potential difference across the terminals. So what is capacitance of a capacitor? It is the what? Quantity of charge stored what? By the capacitor to the what? The ratio, add the ratio, 1 to ready, go. What is capacitance of a capacitor? It is the ratio of the quantity of charge stored by the capacitor to the potential difference across each terminal. 1 to ready, go. Class, what is capacitance of a capacitor? If, wait. If you are not talking, it's a sign of what? A closed mouth remains a closed. Yes, class. What is capacitance of a capacitor? 1, 2, ready, go. The devil is confused. This choir is disorganized. Okay, remove that earpiece. What is capacitance of a capacitor, auntie?
Capacitance of a capacitor can be defined as the quantity of charge stored by a capacitor to the potential difference.
It's okay. Tell your neighbor it's well. So we said it is the ratio of what? Charge to the potential difference. What's charge? Charge is Q. What is the unit of charge? Charge is measured in coulombs. Software? And what is it? Coulombs inverse square law. Now V is what? The potential difference. C stands for the what? Capacitance. Up where? Thank you. Okay. Let us see the factors that can affect the capacitance of a capacitor. The factors that can affect the capacitance of the capacitor. What can you see on the board? C stands for what? Capacitance. A stands for what? Cross-sectional area of the plate. The cross-sectional area of the plate. E stands for what? Eh? E stands for what? E stands for the dielectric material. E stands for what? The dielectric material. And the D stands for what? The distance separating the two plates. Write it. Factors affecting the capacitance of a capacitor. A is the cross-sectional area. Number 2 is the dielectric material. Then number 3 is the distance separating the two plates. Factors affecting the capacitance of a capacitor. Number 1 is cross-sectional area of the plate. Cross-sectional area of the plate. Number 2, let me say, is the nature of the dielectric material. Type or nature of the dielectric material, that is this E. Then, the last one is the distance. We said quantitatively that capacitance of a capacitor is the measure of charge or the quantity of charge the capacitor is able to store. Okay. Then you write again, if you have not known it, increase in the cross-sectional area of the plate, increase in the cross-sectional area of the plate increases the capacitance of the capacitor. Increase in the cross-sectional area of the plate increases the capacitance of the capacitor. Increase in cross-sectional area of the plate increases the capacitance of the capacitor. Y decrease in the cross-sectional area decreases the capacitance of the capacitor. Y decreases. This is, okay, what type of proportionality is this, guys? This is a direct. So as area increases, what will happen to the capacitance? It will increase. As the dielectric material increases, let me use that word, what will happen to the capacitance of the capacitor? It is going to increase. This is direct proportionality. Now, but related to the distance, that's an inverse. So if the distance separating the plates is increasing, distance increasing, what will happen to the capacitance of the capacitor? It will decrease. So write all of them. I know some will ask, Uncle, where are we going to start? Number 1, area is number 1. Increase in the cross-sectional area of the plate increases the capacitance of the capacitor. Why decrease in cross-sectional area decreases the capacitance of the capacitor? That is that thing we explained. Write it. Be an active listener, not passive. Have you gotten that? I go to write the electric material. Increase in the dielectric material increases the capacitance of the capacitor. Why decrease will decrease the capacitance of the capacitor? I am not too fast, I'm sure. I'm telling you what you know. I go to distance. Okay, I write it. Increase in the dielectric material increases the capacitance of the capacitor. Why decrease in the dielectric material decreases the capacitance of the capacitor? Mmadụ edego? Mba. Si ọbụna idego isi mmadụ esego. Mmadụ edego? Mmadụ esego. Okay. Have you written this one? All right, what did you write? Read what you've written about distance. 1, 2, ready, go. Say something. 1, 2. If you're not talking, you're a suspect. Hey, that sister there at the back. Look at me. But I'm not the author and finisher of your faith. I read it. Those people from the back, echo it. 1, 2, ready, go. Distance. Increase in distance separating the two plates. Be articulate. Ahead does what? Decreases the what? While what? Okay. We'll come back because we need to explain everything here. Very, very important. We'll come back here and explain something, but let me go to the energy stored in a capacitor. Right, energy stored in a capacitor. Energy stored in a capacitor. Work done by a capacitor. And the heat dissipated. What is the unit of energy, class? Class what? Joules. Where? That's J. So energy is the same thing as work done, and it is the same thing as what? The heat dissipated. Now, in your mechanics, work is what? The product of what? Force and distance. Correct. In electricity here, the work done by a capacitor is charge. That's the average of charge and, okay, is charge times potential difference over 2. The average work done is charge times potential difference. You can write it like this. W is half QV. Is that okay? And this thing is the same thing as QV over 2. You call it equation 1. Now, for us to get equation 2, look at the board here. Stop writing now, sec 3. What is capacitance of a capacitor? It is the ratio of what? Charge to potential difference. Can I make charge the subject of the formula? So what is charge? CV. So you have a CV. Now look at this equation. Equation 1. Anywhere we see Q, what should we write? Those people at the back, look at me. Look at the camera. Anywhere you see Q here, what are you going to write there? CV. All right, let's replace. Follow me. Talk. CV. No, CV times V over 2. Don't be too fast. Which is what? CV squared over 2. Equation 2. Don't write. You will reach equation 3. Okay. From this equation again, I can't see don't write. Can you make V the subject of the formula? Yes. Eh? Yes. So what is V? V equals what? Q over C. So what are we going to do? We are going to sub V equals Q over C in equation 1. Is that okay? So anywhere we see V here, what are we going to put? Q over C. All right, let's do it together. Make sure, just don't write. Look at the board. Make sure. What should I write? W Q V over 2. Let's replace W equals. Okay, are we replacing Q? Eh? Q times, I'm replacing V with what? Q over C. So anyway, I see V, I can write Q over C times what? Q over C, all divided by 2. Is that okay? Don't write, Oga. Just don't worry. W is what? Oh yeah. Q times Q. Q squared over C, all divided by 2. Is that okay? All right, let's still break it further. Let's come here. W is what? Q squared over C divided by 2 over 1. Up here? You don't understand? Auntie says she don't understand. You understood. W is what again? Q squared over C. Okay. Times what? 1 over 2. Which will give you what? Q squared over 2C. Equation 3. You can copy. Okay, should we progress? Is that okay? Okay. Should I clean the board? Auntie, snap your screen. Okay. Without controversy, can you give me the formulas for the energy stored in a capacitor? Number one. Hey, look at me. What is the problem? Hey, don't look at your work. I'll fight you like virus, Oga. Look at me. Oh, yeah, give me the formulas for the energy stored in a capacitor. Number one. If you are not looking at me, I don't know. W is equal to what? Half QV. Number two. Again. Number three. I close your eyes. Say it on your own. Don't look at your material. Number one. 1, 2, ready, go. Wait. I caught this girl. Say it again. 1, 2, ready, go. Again. Number two. Shame your village people and tell them the third one. 1, 2, 3. Open a neighbor gine na ya na akwụkwọ ya. Say a neighbor receive sense. Yes, you should say it extemporaneously. Okay, how many of you can say it without looking at your material? You can say it. Or you say it again to the shame of the devil. 1, 2, ready, go. Uh-huh. Uh-huh. Amen. Okay. Practical uses of a capacitor. Practical uses. Remember I said we are still going to fall back to this guy. I want to explain something there. Practical uses of a capacitor. Now, by default, we know that a capacitor can be used to store charges. Up here? So I will not say that one. Capacitor is used together with an inductor in a radio circuit for tuning. Capacitor is used together with an inductor in a radio set for tuning. For tuning. Tuning. You know, that time, if you have those old radio, you'll be turning the knob to get 92.7, where you meet in Namen. So the capacitor works with the inductor in what? Tuning radio set. Or you can tell me one practical use of capacitor you've known now? It is used in radio sets for what? Tuning. Okay, number two. It is used in the ignition system. It is used in the ignition system. Ignition of motor vehicle. It is used in the ignition. It's only you and your book that know what you spelled. It is used in the ignition system of motor vehicle. See, your daddy will on the ignition of the car. Number three. Is it number 4? Okay, number 3 or 4. Capacitors are used to reduce sparks in systems that uses induction coil. Capacitors are used to reduce spark in systems that uses induction coil. Are we together? Tell me the practical uses of capacitor. Number one. Number two. Number three. That uses what? Induction coil. Okay. So what are the factors affecting the capacitance of a capacitor? What? Cross-sectional area. Number two is what? And the third one is what? All right. Relative permittivity. Let's return to this. Relative permittivity. In bracket, dielectric constant. Relative permittivity. It's only you that will spell that permittivity. Relative permittivity. Find out now. It's double T. It's double T. In bracket, the old name is dielectric constant. Dielectric constant. So when we talk about relative, what are we talking about? Relative motion, you are trying to compare the motion of a body with another body. Relative density, the weight of water with something else. Anything relative, your relation, you want to compare two things. All right, relative permittivity is the permittivity of a material. Is the permittivity of a material expressed as a ratio with the permittivity of a vacuum. Expressed as a ratio of what? As a ratio with the permittivity of a vacuum. All right, class, what is relative permittivity? Again, what is relative permittivity? Okay, right again. Permittivity is a measure of the polarizability is a measure of the polarizability of a dielectric material. So class, what is permittivity? Again, what is permittivity? All right. A material with high permittivity will polarize more in the presence of applied electric field. I read what I said now. 1, 2, ready, go. A material with high what? Permittivity will polarize more In the presence of what? Applied electric field. Thus, storing more energy. Thus, storing more energy. Idegia. Right again. A dielectric under it. A dielectric is an insulating material. A dielectric is an insulating material. You put a comma. It is a poor conductor. It is a poor conductor of electricity. It is what? But. Write but there in capital letter. But an efficient support of electrostatics. Idegia. Idegia. Full stop. It can store charges. It can store charges through polarization and it possesses a high specific resistance. A high specific resistance and negative temperature coefficient resistance. So where they go? I read what you've written. Eh? A negative what? A negative temperature coefficient of resistance. A negative temperature coefficient of resistance. I read what you've written thus far. Start from relative permittivity. Uh-huh. Okay, this question will take us to JAM 2006, number 23. Question number 23. 2006, question number 23. But let me explain something before the question. In between the parallel plates of the capacitor, what do we see there? Eh? We see a dielectric material. Remember that this capacitor have two terminals. It have two terminals. In between this thing, we have what? A dielectric material. And this dielectric material, you know, okay, if this is in a complete circuit, charges will move or current from here. This insulative material, okay, let's say this is positive, this is negative, it will prevent the charge from touching this one. Are we together? Because this is an insulating material. But dielectric materials, we call them an insulating material, but they are not actually insulating material. They are actually poor conductors. Yes, normal physics call it an insulating material. Yes, we know they are insulating material, but they are not insulators. What is the work of an insulator? An insulator do not allow what? Charges to pass through it completely. An insulator, charge cannot pass through it. But for dielectric material, it is working as an insulating material, but it is not an insulator. It is a poor what? Conductor. So once the charge is CBEBA, two of them will not touch. There will be a high polarization effect. Now, because of the polarization effect, charges will be developed by electrostatics. Because of the polarization, charges will be developed by what? Electrostatics. Now, those dielectric material will now absorb those charges or trap all those charges and hold charges for some time. That is why we said that capacitors what? Stores charges. How do they store charge? They do not allow the charge to move from here to here. The charge did not leave that circuit. Now, a polarizing effect was created, and the insulating material now what? Trapped it. So those insulating material, like in paper, capacitor, it can be a paper, it can be wood, it can also be what? A vacuum. It can also be what? Now, listen, when this is a vacuum, E naught. Now, what is E naught? Permittivity of what? Free space. Permittivity of what? Free space. Now, if a capacitor, if the capacitance of a capacitor in a vacuum is 2 microfarads, if I add a dielectric material to it, it can be wool, it can be 6 microfarads, or ceramics. It can be 6 microfarads. Now, what is the work of the dielectric material? What did it do? It increased the what? Capacitance from what? 2 microfarads to what? 6 microfarads. Okay, yeah, but those things. Dielectric what? Material. In that space, dielectric material nearby. Permittivity of what? Now, what is permittivity? Go back to your note. It is the measure of what? Thank you. Now, what is a dielectric material? Is an what? Insulating material, comma. It is what? Now, is it not so confusing? It's an insulating material and also what? It is working as an insulating material, but it's a poor conductor. If it is a complete insulator, there will not be that polarization effect. In fact, charges will not be developed by electrostatics. But because it is a poor conductor, it can trap those charges developed by electrostatics. Now, where do you see those these capacitors? Most times in your charger head. Okay, I think it have charger head is in your fan. Even though the fan is an inductive load, it has a capacitor. At times you discover in your charger head, they will take light, but the small lights will be on for some time. It has capacitor inside, so it can trap charges even when the source have been removed. So imagine we developed a super capacitor. That means that one can last for what? Hours. So what is the function of the capacitor? To store what? Charges through this polarization effect. Are we together? Now, relative permittivity or the electric constant, it is now when I say, let me compare the material and the what? Air. The material and vacuum. Okay, read your notes. Read the first thing. Relative permittivity. What is it? What is relative permittivity? Is the what? It is the what? It is the permittivity of a material. So permittivity is represented with epsilon. Eh? Epsilon. Okay? Yeah? So if it is 0, epsilon 0, that means permittivity of 0 is a free space. So if I write it M here, it is the permittivity of what? Medium. Now, every medium, every material have their own permittivity. Is that okay? Would you agree with me? Ceramics and plastic will not have the same permittivity. Okay. Now, the permittivity of the material I am using over the permittivity of free space, which should be about 8.85 times 10 raised to the power minus 12 farad per meter, is standard. Is a constant. Now, permittivity of this thing divided by the permittivity of free space will give me what is called what? Dielectric constant. So what is the electric constant? Permittivity of the given medium over the permittivity of what? Air or free space will give me what is called what? Dielectric constant. But I told you dielectric constant is an old name. The best thing to call it what? Relative permittivity. Because we are checking the permittivity of two medium. The medium and air. So when you tell me that A is equal to E over D, so what would you call this E now? What is air? Relative permittivity or permittivity of the dielectric material. I'll call this in a dielectric material. Then when do you call it a constant? If they give it to you as a constant, that means it has been checked with vacuum. And you call it dielectric constant or relative permittivity. Check JAM 2006, question number 36. Check, let's be sure of what we are saying. Remember I said different material have different what? 2006, question number 23. Check. Different material have different permittivity. When the permittivity is in vacuum, we call it permittivity of what? Free space. And what is permittivity in your note? Is it there? They say the capacitor of so 2 microfarads, something 6 microfarads. Find the dielectric constant. 2006-23. Am I okay? Have you seen the question? Or you give me your prep. Let me search for it. Go to capacitors in your prep. We'll see it there. Have you seen it? Give me your prep, or if you have all-inclusive calculation, it will help me trace the question. Is it there? Have you opened it? Do you know the question number? Number 22. That's 2006, number 32. Don't mind me. A sign of senility. They said, the capacitance of a parallel plate capacitor when in air. I write it. The capacitance of a parallel plate capacitor. The capacitance of a parallel plate capacitor. In fact, if you don't want to call it parallel, call it P plate before you commit blunder. The words. The capacitance of a P plate capacitor when in air is 3 microfarads. Madedego. When in air is what? 3 microfarads. And in the presence of a dielectric material. And in the presence of a dielectric material, it is 6 microfarads. What is the dielectric constant? 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 Did you get the question? All right, read it. Read it if you got it. 1, 2, ready, go. Close mouth. What is the what? Attack the question before the question attack you. Is it 2? Yes. So what are we asked to find? The relative permittivity, which is the same thing as the electric constant. So the relative permittivity, okay, use this formula. Okay. ER, EM over E naught or E air. Oh yeah, what is the permittivity of the material? 6 microfarads over air. 3 microfarads. Remember, anything relative have no unit. The electric constant, no unit. Microfarads will cancel microfarads. 6 divided by 3, 2. So what is the answer? 2. Ask one, 2 microfarads. The answer is just what? 2. Relative permittivities. Class, what is the electric constant? 1, 2, ready, go. What is the electric constant? 1, 2, ready, go. Thank you. You get it. You relax. So a material that have a high permittivity will likely be very polarizable. And when its permittivity is high, that means it can store more energy. It can store more charges. Is that true? So different material have their different permittivity. Different material have their different what? Okay, they say that. Okay, go to F is equals to what? Q1, Q2 over what? 4 pi E naught R squared. Okay? Now, what is that E naught there? Permittivity of free space. That, do you know this formula? Yes. Sunday. Hey. That's force, electric force, Q1, Q2 over 4 pi E naught R squared. Now, I am now asking, what is that E naught? Is it just permittivity? Permittivity of free space. I don't want, anytime you hear permittivity, you be misplacing it with the electric constant. It doesn't make sense. Is that okay? So, you've seen the factors affecting this, the capacitance of this capacitor area, the dielectric what? Material. Only material you can use or may increase the what? Capacitance. If it is air, will the capacitance be high? So, only material you use, when the dielectric material is of a good quality, the capacitance will be what? High. Now, look at the capacitor. You know, this is the actual capacitor. The thing here, oh, it is not these two things. These two things is helping to cause polarization so that charges can be developed here by electrostatics. Look at the capacitor. If I remove this thing inside, what will be here? A vacuum, permittivity of free space. If I have a good quality and it is big here, what will happen to my capacitor? My capacitor will be thick. I can have 10 microfarads. If I decide to remove, I can have 2 microfarads. Now, between 10 and 2 microfarads, which one have a higher capacitance? Now, what is capacitance? The ability of the capacitor to what? Store charges. So that means if we have a supercapacitor, you can use it to power your house. It will store, and power the house. Okay. Next, we said the uses of capacitor. Now, in induction, in a system that uses induction coil, what is the work of capacitor there? Oh, my father, my father. In systems that uses induction coil, those guys at the back, you can see me. What is the work of capacitor there? To reduce spark. How can we arrange capacitor in a circuit? Can they get GTC then? This over and confused. You want to be a nurse, you want to be. Come, let's arrange capacitors. We can arrange capacitors in what? Series and what? Say it. In series and what? But that is a national anthem. Do you know what is happening there? If we want to build a circuit now, I see that we need 1 microfarad capacitor to build that radio circuit. And I entered your studio or your workshop. I saw 2, 3, 4, 5, 6, and I did not see one. Is there anything I can do to create my 1 microfarad capacitor? That is called the arrangement. It is like a formation. Last night, or yesterday, K formation Nigeria bar. You don't know the formation? Can they bet? I'm no Maya. 3 guys, come. Let's arrange capacitors. Let's arrange capacitors. You know what we used to denote a capacitor? Remember, these 2 things must be equal. They must be what? Equal. This is capacitor. What do we use capacitor to do? Store gene charges. Oh yeah, 2 guys, 3 guys. Do you need me to call you? But I'll say so. Teacher love letter. Okay. Where's the third person? Oga? Let's arrange them. All of them are varied. There is no constant there. Is that your question? Oh, from the back. Okay, we have these 3 guys standing. He is a 2 microfarad capacitor. Oh, I see. Hold your hand. Hold your hand. What type of arrangement is this? You know, this is a serial arrangement. Now, when capacitors are arranged in series, what happens? Their effective capacitance, their what? Or their combined capacitance is given out. Okay, when they go, then I'll start writing those ones so that they won't obstruct us. Now, this is a serial arrangement. You see, this guy hooking this guy this particular way. If I join them, I'm still in series with them. Now, I want you guys to arrange yourself in parallel. Front, middle, back. Hold yourself. No. Bring out your hand. Hold here. Hold there. Hold there. What is the arrangement of this capacitor? What is the arrangement here? Parallel. What is the arrangement the other time? Series. Now, okay, go back. Let's start with parallel. When capacitors are arranged in parallel, their effective or combined capacitance is given by 1 over C effective, 1 over C1, plus 1 over C2, plus 1 over C3, plus 1 over C infinity. I say when capacitors are arranged in parallel, they are combined. Oh, you know what is parallel now? They are combined. I say let me start with parallel. Sorry, Sunday. Sorry, I didn't look. When capacitors are in parallel, their C effective is C1 plus C2 plus C3 plus C infinity. So sorry. This is the parallel arrangement, which is the opposite of resistor. Their combined capacitance is C1 plus C2 plus C3. So in the diagram above, what is the effective capacitance? C1 is what? 2 plus 3 plus what? 4, which is what? Which is what? 9. Sorry. See what I meant? See what I meant? This is 2. This is 3 and what? And what? 4. Second point. C1, C2, and C3. C1, C2, and C3 have the same potential difference. C1, C2, and C3, that's C1 to infinity, have the same potential difference. They have same BD, same PD, in brackets, voltage. Different, but different charge. But different what? But different charge, Q. The total charge is given by total charge Q is given by Q1 plus Q2 plus Q3. You can have Q infinity. Where Q1, okay. So Q1. Okay. Okay, leave it like this. All right, what do we see for capacitors in parallel? What do they have? They have the same, but different what? They have the same what? But different what? Charge. The total charge is Q1 plus Q2 plus Q3. Okay. Go to serial arrangement. Just compare and contrast. We end there. Capacitors in series. Now write for capacitors in series, the C effective, the C effective, the C effective is 1 over C1 plus 1 over C2 plus 1 over C3. Okay, plus 1 over C3 plus 1 over C what? Infinity. But for two capacitors in series, the C effective can be given as C1 times C2 over C1 plus C2. But for two capacitors in series, the effective capacitance, C effective, can be given as C1 times C2 over C1 plus C2. You don't put 1 over C again. If you like, you can still put 1 over C, but it will be easier for you. For 3, if there are more than 2, you use this formula. If there are just 2, just do C1 times C2 over C1 plus C2. Even though this one can still give you the answer, but this guy will be faster. Is that okay? Okay. Now, capacitors in series have the same charge. Say C for C. Yes, capacitors in series have the same charge, but different what? They have the same charge, but different potential difference. Write it. They have the same charge, but different potential difference. Have you written that? Eh? Have you written that? Okay. Let me ask you questions about capacitors in series and parallel. What do they tell me things about capacitors in parallel? Their C effective is what? C1 plus C2 plus C3 plus C infinity. What do they have in common? They have the same potential different but different charge. That is the two most important things. Forget about this guy. When we solve, we'll talk about that one. Now, for capacitors in series, what is their C effective? 1 over C plus 1 over what? Echo it from the back. Plus 1 over C. But if you have two capacitors in series, you just say C1 times C2 over C1 plus C2. What do they have in common? They have the same what? But different potential difference. Okay. You are going to solve 4 practical questions. No, you don't. Now, it's not my class. Of course, we give you 30 minutes break, meaning that we're going to dismiss you to 30. Status quo. I wish you know. You people were begging for 30 minutes break. I've given it. If you can return to 5, it's a normal thing. Just pipe. All right, take this question down. Before you take that question down, use 5. Okay, use 2 minutes. Scan through your work. Use 2 minutes and scan through everything we've said thus far. From the definition of capacitor to permittivity to capacitors in series. Okay, somebody give us a question. The assignment. Let's solve this. Hello? What is the arrangement of these capacitors? Eh? They are in series. They are in what? Now, since they are in series, listen, what would they have in common? Eh? Eh? They have the same. They will have the same charge, but what? Now, what is the potential difference here? 12. Would this one have 12? No, now. Will this one have 12? So the 12 will be shared among them according to their capacitance. But what do they have in common? They have the same charge. So the first thing is to find the effective capacitance. The first thing is to find the what? Effective capacitance. And what is the arrangement? So C effective. 1 over C effective up here. 1 over C effective is what? 1 over C1 plus 1 over C2 plus 1 over C3. Somebody asked me, Uncle, I thought it's 1 over CT. 1 over C1 plus 1 over C2 plus 1 over... Are they not the same thing? This is C total now. This is the effective. This is even the best language to use. Okay. What is our C1 there? 2. Help me. Talk. Eh? 1 over? Yes, 1 over what? Okay. Now what is the LCM? The LCM is what? 2 into 6 times 1. 3 into 6 times 1. Total. 6 over what? 6. Even if I invert it, it's the same thing as... Okay, so it means that... This means that 1 over C is 6 over what? 6. Up here? So what is C now? C effective. C effective is 6 over 6. Even if I invert. And what is 6 over 6? 1. So the C effective is what? 1. The C effective is what? 32 people are confused. If you're among them, raise up your hand. Okay, where is the source of the confusion? I was tracing the source. From here, where? Sister, from where? Is it the formula? Okay, 1 over 2, 1 over 3, 1 over what? 6 they gave us. Eh? And what is the LCM of 2, 3, and 6? Oh yeah, 2 into 6, 3. 3 into 6, 2. 6 into 6, 1. You add it. Can you get what there? 6 over 6, which is 1. Okay? Yeah? 1 is 1. 15 more people are confused. Okay. So, I have my C effective to be what? 1. Let me find the total charge. We'll find the what? Total charge. Now, listen, look at the board. What is Q? Q is CV. Q is what? Now, the total, okay, let me use Q like this. What is this? What is C? Eh? C is capacitance. That is the effective capacitance. All right, look at your screen. What is the effective capacitance? Ask your neighbor, what is effective capacitance? So, C is what? 1 times what is V? 12. Given. 1 times 12. 12 what? Oh? Coulombs. What is the unit of charge? 12C. Now we are asked to find the PD, the potential difference across the 6 microfarad capacitor. What are we asked to find? The potential difference. That get right in. Do you want to study secretarial study? What are we asked to find? Across what? Now, they are in what? They are in what? What do they have in common? They have the same what? They have the same charge. So, what is the charge here? What is the charge here? 12. The charge here is 12. They are in series. C for C. Series for charge. They are in series. C to C plaza. Series for what? Charge. So parallel will now be what? Potential difference. Are we together? So what is the charge across this guy? What is the charge across this guy? What is the charge across this guy? What is the total potential difference? Will they have the same potential difference? Will it, if you say it's 12, 12, 12, attack. They have different PD because they are in what? Series. So for me to find the PD of this guy, I am still going to go back to Q equals to what? CV. What is my Q? 12. What is the charge? Eh? What is the capacitance? What is C? Eh? What is, I'm looking for the 6 microfarad capacitor. I'm looking for the what? 6 microfarad capacitor. So this is going to be what? C. Times what? Times what? V. Because we are looking for V. Okay, yeah? So, and this is going to be V is what? 12 over 6, which is what? 2 volts. So the potential difference across the 6 microfarad capacitor is 2 volts. Now do it yourself. Find the potential difference across the 3 microfarad capacitor. Eh? Eh? So what are we going to do? Q is equals to what? CV, which is 12, 3 what? V. So V is going to be what? 12 over 3, which is what? 4 volts. Okay, yeah? Now, what is the potential difference across the 2? It is going to be what? Do you know why it is this? 32 of them don't know why. So I'm going to write here 12 equals 2V. So V is what? 12 over 2, which is what? Oh, 6 what? Oh yeah, add. 6 plus 4 plus 2. Did he give us 12? What is the total potential difference here? The potential difference here, Nkokwan. Eh? The potential difference here, Nkokwan. The potential difference here, Nko. The charge here. The charge here. The charge here. The potential difference here. The potential difference here. The total potential difference. And what arrangements are they? What do they have in common? What is fighting them? Attack. They're under attack. I take this last one. Jam 2000. Oh God, that thing is going to jam you. Let's change it. Where should I clean? Practice question. Find in the diagram above. In the diagram above. This is 10 microfarads. Calculate the energy stored. Calculate the energy stored. Calculate the energy stored in the capacitor above. This is 10. Don't mind my handwriting. In the diagram above, if you're at the back, come and show me your paper. In the diagram above, help me find the energy stored. The energy stored in this capacitor. Flipping through the pages of this great book. Somebody's turning backwards. Made, there go. Find the energy stored. Find the energy stored. Find the energy stored. In joules, please. In joules. In joules. In joules, F9. In joules. Remember to convert your microfarads to farads. Remember to, oh, you are working with 10 in this dispensation. Rapture is waiting for you. Dangerous and activated. A1 smashed. F9. Check. Just more. Dangerous people at the back. Show me your work. F9. I want to see your work. Energy stored. Don't make the mistake of working with 10. A1 smash. Dangerous answer. A1 smashed. F9. Bro, let me see your answer. Let me see what you're doing. Lay your hand on your head. So I receive sense. More sense. If your neighbor is writing solution, say a neighbor go. A1 smash. May you never sit close to a neighbor in an exam hall that will write solution. Or that will see question in the computer and start copying it out. Call Diego. And Jesus wept. You already know that the energy stored in a capacitor. What are the formulas? E is what? Half CV squared. Alright, let's start from E is equals to what? Half Q. E is equals to what? Is it not it? E is equal to what? Q squared over 2C. That is the formula for the energy, heat, whatever. Work done. Now listen. This is 10 microfarads. We need to convert it to what? Farads. Please. So what are we going to... Okay, C is what? 10 times 10 raised to power minus 6. Oh, change you go to farads. Konema, bro. You don't know before. Okay. Now what is V? 12. What are we asked to find? E. Oh yeah, look at this formula. Which one are you going to use? Are we going to use this one? Because charge is not given to us. Are we going to use this guy? There is no charge. Are we going to use this? Oh yeah, let's try. E equals C is what? 10 times 10 raised to power minus 6. Times what? 12 squared, which is 144. Okay. Times 12 what? Squared. All over what? 2. Do your thing now. 10 times 10 raised to power minus 6 times 144 divided by what? 2. 2 divided 144. 72. 72 times 10 raised to power minus 6 will give you what? Is that not the answer? Okay. We are going to call it a day if you want it to be a day. Capacitors are used mawagente. You people are just learning. Okay, 32. It's well. Tell your neighbor it's well. Please. I know you have been feeling rubbish in that form I gave you to fill your jam form. But I want to tell you what to do now. Tomorrow is Saturday. Please, and if you have gotten your profile code, reappear here on Saturday. Remember, we still have classes for YX students. But if you can't make it tomorrow, but make sure I want to see your form before placing the registration. I know why. Invite your friends to register with us. They should not come here. They should just go to our satellite center. Now, your first choice, I know I'm addressing medical students here. Medical, you can be nursing, pharmacy, med lab. Please, why choosing? Be intentional. I don't know. I'm going to give me a privacy forum. I want to tell you something that will help you so you can get admission faster. Before I tell you to choose a university, I will check the state you are from and to know whether your state is among the catchments of the university you are putting. Please, don't just put anything. Your first choice, choose the federal university and state university. They are in the same category. Do you get? Whether they are same, your second choice, as a matter of fact, matters not. But yes, if you want ESU to be that ESU to one, make ESU your first choice. Don't go make ESU second choice. It is not those days federal university have to be at as the first strata. Even if it's private university, it can be at the first strata. University is university. Choose federal university if you want. Secondly, the second choice, you can choose a state university, but no, it's your first choice that matters. Now, the third level, use polytechnics. Is that okay? You will not go to polytechnic, amen. But you must have to feel it. Don't go write UNN again. The system will reject it. Is that okay? Choose a polytechnic. You can use IMT. Choose Science Lab Tech. Finally. That is the only one close to you. Science Lab what? Tech. Now, for the fourth choice, let's go for a monotechnic. Colleges of Nursing. But now, UNTH is not in the site. I can only see College of Nursing Amici. Though they are doing everything to make sure they add UNTH, NEWI and other things. But even if they don't add them, just choose college or any College of Nursing you see at that fourth choice. Monotechnic. At that fourth choice. Choose College of... Don't go and write... If you write UNN there, you will just cancel your form. We have to tell you to what to... Just at that fourth level, write College of Nursing Amici. Now, when UNTH appears in the portal or whenever they decide, you can do change of whatever, institution and everything. By then, UNTH will be there. But for now, you don't see UNTH there. And remember, before you enter schools of nursing from 2024, you must write JAM. You must buy JAM form. So you can even buy JAM, fill anything, even if you are not interested. Make sure you have JAM form. Because that will be a ticket for you to get forms to School of Nursing. Don't just fill anything. Be intentional in what you are doing. Can we stand up and share the grace? Please, YX students, remember we have FPPC class tomorrow. If you have your profile code, I don't think you should leave here without seeing me. Let me be sure I'm registering you today.